Um, my name is Icaro, as Gustav said. For those who don't know me, I worked in round two as a delegate, um, especially during release work. And among other topics, I was responsible for some of those connection control procedures in RRC. And that will be, let's say, the first part of this presentation where we try to cover some aspects of these subtopics, RRC states and some of those state transitions and some other procedures that we have also worked in round two. I would like to start this showing and sharing with you a book I recently read, which is about sleeping, and it's written by a sleeping expert. And I'm not sure if it's because he sleeps a lot, but at least he has been doing quite some research and studies on that. And one of the things that this book talks about is that while we sleep, our brain is very active and sort of prepared to wake up. So for those who have read anything about this, we have those REM and non-REM cycles. And basically, we have some sort of switch between those cycles while we are sleeping. And one of the points he makes in the book is that when we are asleep, we are not shut down at all. There are many things that happen, and he tries to make a point of the importance of sleep and why it's important for memory and stuff. And as a 3GPP delegate and having some jet lag, we get interested in those things over years. But the point is that we will talk about those sleep states in RRC, and there also one of the things I learned at the very beginning when I started to study this is that many things happen when we say the U is in sleep state. Of course, it's not as optimized as this connected state, which is mainly for data activity and a lot of things. It's more for power savings, but many things happen. And this was one aspect I thought was interesting to bring it up and how important this is. But also this thing of always being prepared to be awake, and usually sleep is in the second part of our sleep, which is also very important for other things. We are more prone to be awake usually. And that's very important also in these RC states, that everything or many things that we configure the UE when the UE goes to this sleep state, it's somehow aiming that when the UE comes back, this is very efficient. It has to be quite fast and low signaling and so on. That's why I thought this was interesting to bring it up. And the main goal of this presentation is to talk a little bit on some principles of these so-called RRC states and those transitions from sleep states to connected, and some of these other connection control procedures. Why is this important? I guess if some of you that are not so familiar with Run 2 asks, I guess basically this is affected by any Run 2 feature that you would standardize in the future. And this was a little bit of a bold statement. I'm not 100% sure, but I think it's a fair statement to say for those who have worked with RRC that at least one of those procedures will be affected by anything you will standardize, or at least most of the features you would standardize. Another reason is that this is likely to be implemented, at least it is in our roadmap, and at least some of these are optional, but it is in our roadmap, like the inactive state procedures. But I guess some of them are very, very, very basic. We cannot build an NR standalone network without having state transitions, for example. Another reason, a bit of a more historical background, is like this is specified in RRC, where we are rapporteurs, and we have also contributed quite a lot. And some of these procedures, they are actually based heavily on Ericsson concepts that we have developed even before NR standardization start, or even before that from LTE that were borrowed from LTE. That was also something recognized as being brought up by Ericsson, or Ericsson perceived that. So those are sort of examples of reasons why this is an important thing. The approach taken here is like sometimes we will go with some overviews of basic concepts that some of you are aware. And the reason is that we have some people who are not very familiar with the LTE procedures to a certain extent. And sometimes I try to go to what I call here deep dives on this delta. This is important to say. And what I call delta here is basically that NR equals to LTE plus delta. I guess one of the first agreements we have had from the beginning of an R standardization run 2 is like LTE is baseline. So it's quite funny because anything we wanted to get agreed, we just need to start the statement saying as in LTE, and whatever you write has a higher likelihood to get agreed. But it is partially because people are happy somehow with the way LTE RRC was standardized. So of course we would sort of borrow many things which happened in LTE that were happy and try to improve other things. So in this presentation, I will spend maybe a bit more time on these delta things. What is different from LTE? Which means I would omit some things that are just like LTE. So anything that you feel is omitted is probably because it is as in LTE. So RRC states, so the first thing to say is that as in LTE, RRC specifies the UE actions per state. So basically saying how the UE does mobility, how the network contacts the UE, how the UE contacts the network, what the UE does in this and that situation. Usually we say this depends on the state the UE is. So mobility is a classical example that in sleeping states, either inactive, we have this UE-based mobility. In connected mode, we have this network-based, which means network needs to know where to go and so on. Then we have this connected state, which is mainly optimized for data transactions. And when the UE is already in this connected state, you may be released or suspended by the network. We use this terminology here. Released to idle or suspended to inactive. We have these two sleeping states that we call inactive and idle, which is mainly optimized for power savings, but I was trying to explain in this analogy I was making with the book, it should support a fast transition to connected, but also efficiently in terms of signaling. I will go a bit more into details later when I explain the transition procedure. I guess the main new thing here when it comes to the overall states and the architecture is that this RRC inactive was introduced in NR. We have that in LTE, and I put that as sort of as an evolution of the LTE release 13 solution for those familiar with that. But later on, it became a bit more confused because LTE also adopted this inactive state when connected to 5G core. You have seen the presentation last time about these different architectures, and it becomes more complicated. We will not go too much into that, but I would touch upon this evolution of release 13 aspect. What is different from this release 13? This is basically the machine that we will go through in this presentation. So we'll talk about most of these procedures here, idle to connected, inactive to connected, and so on. So let's start with the idle to connected. So this is basically used in many different contexts, but I guess the most, let's say the simplest one to start with is when you turn on your phone. So basically you are starting from an RRC point of view in idle, but then you immediately go to connected. And the reason is that you got to sort of register with the network, mainly with the core network. And in order to exchange information with the core network, you have to first set up a radio connection, and that is done through this RRC connection. This is one of these procedures which is very similar to LTE, except some message names. So I guess this is the main thing I could say. And there are, of course, some new aspects which can be said to come from this 5GC design, such as this network slicing. If you have heard presentations about 5G architecture, you probably heard about that. But that does not affect very much the way the UE behaves from a RAM point of view or from a RAM 2 specification perspective, except that it changes the way you do the idle to connected transition. So if you focus first into the right-hand side of the presentation where you have the signaling flow of the procedure, you will see in this first red box the three messages being exchanged. You have this setup request where the UE includes an identifier and some establishment calls, and then the UE responds with an RRC setup and this RRC complete. And after message 2, the UE is basically considered to be in connected mode. But not much happens at this point. And the first sort of set of differences compared to LTE is that in the request, we have this 5G STMC, which is a 48-bit, which is larger than in the LTE case. And then here what happens is that we actually split that into two parts. And the first part is sent in the setup request, while in LTE you can include the whole identifier. And the reason has to do with, let's say, a last minute thinking run 2 while we were standardizing this, and we have agreed on a certain identifier size coming from other groups. But then run 1 has pushed somehow a certain limited size of message tree, and that would not fit. And this is transmitted in a channel that is not sort of flexible in terms of expanding. So then we had to live with that, and then we came up with a solution where we would split this into 2 parts. Another new aspect.
Icaro, a question about this split. So when is the second part sent?
We will get there, but you could guess.
In the complete, or?
I mean, yes, exactly. And then we have, again, in this first message, you have these different establishment causes. Most of them are like LTE, but we have this MO video call that is new in NR, and this delay tolerant access is not supported in NR. Then we receive the setup, and that is where the UE actually could say it to be in connected mode. And as in LTE, this is just a setup of SAP integration. But at that time, even though the message supports a lot of different signaling because of the structure, there are a lot of restrictions you will see in RRC because you haven't yet started security. For example, this message includes these 2 IEs, this radio bearer config and cell group config, which is basically a very generic structure that goes in radio RRC setup, RRC resume, and RRC integration. But in this particular use case, not all of these could actually be transmitted because security is not started yet. So basically, the only thing you can do is to start a SAB1, and not even there you can do much about it. It's only the PDCP config, and only there it's very limited information you can actually configure. So it's almost empty. I assume that Henning or Patrick will go a bit more into the details of that structure and how this is actually changed from LTE, where they have this radio resource config dedicated or something like that, for those more familiar with the LTE RRC. And then you have this cell group config, which is basically consisting of the set of UE specific and cell one parameters, which will also be explained in the follow-up presentation. But here again, when you read RRC, and that is a very common exercise we do, we go for the messages, we see that the IEs are there, but you see these conditions also, where there are a lot of restrictions what the UE actually expects to receive or not in the different messages. Even though the IE and the signal is somehow there, it's something good to think about. I think, in touching upon this topic, since this is sort of round 2 seminar, I think it's sort of it could be a bit confusing when you are not very familiar with this to see, but the signal is there, so can't the UE receive? So it's very typical to see these restrictions in some common IEs. Then it comes the setup complete, I guess. After the UE is in connected mode, you'll set up a SAB1. And this setup complete actually contains the remaining 9 bits of the 5G STMC. And it also includes some slice information, which is basically a list of selected slices. And this is not really specified in RRC. And this is another thing which happens very often, that sometimes we just capture in RRC like this is selected according to NAS specifications. We point to specifications and we just have the signaling in RRC, or not even the whole signaling, but sometimes it's just a transparent container, such as in this case of setup complete, where, as you can see, this is first time the network connects to with the core network. So this also includes a NAS PDU message in a transparent container. But that, like as in LTE, as I said. So the new aspect is this remaining 9 bits, and this is slicing information. Then the procedure goes on, and there are some exchange of messages with the core network and the initial context setup between the run and the core, which basically exchanges information about this UE that could be retrieved, for example, from the subscriber database, and then the core network tells the run capabilities and so on. And then you go for this security mode command, which is the initial security setup. So this is an important timing in this IDO2 connected procedure, because from that point onwards, there are lots of RC procedures that could actually happen, which basically means that there are a lot of that cannot happen until security setup. So when we go through RC, you will find a lot of reference about this can only be sent after security is initiated. That's a very common statement at the beginning of many procedures, such as measurement reporting. And that's why it's very important, this timing. And this is also very important when I explain a bit this inactive to connected, because that is the step which is skipped because of the inactive state.
May I ask a question?
Sure.
About the slicing for here, so is included in the message file in form of another NAS video, one IE NAS video, because we already have a NAS video.
Yeah, it's actually a good question. I mean, it could have been included in the NAS PDU because it is a NAS sort of selection function, but in this particular case, it is a RRC IE. But then what we say is like NAS provides to RRC, we include the NSSIs that have been provided by NAS according to the NAS selection.
Could have been included as some IE in the NAS video, which is already there, right?
I think the reason in this particular case is that it is about the run knowing those. It's not about the AMF knowing. So that's why it's included. That's typically how this is designed, I guess. One different thing also from LTE is that in LTE, every time you do this idle to connected transition, you will always end up having this number 8 step, which is a reconfiguration, where basically you can configure anything. But I guess the basic thing that you have to configure in LTE are the SRB2 and the DRBs, which is actually for data transmission. But then in NR, you need to have this signal-only connection where this step is not mandatory. So you may end up actually in step 7.
Can you reconfigure an SSI in step 8?
No, actually an SSI is not really something that you actually, at least my understanding is that it's not something that you actually reconfigure. It's something that is either based on some selection, based on what is broadcast or something in the SIM card. Me and Gunnar, we were trying to dig that yesterday. It's a fairly complicated procedure on NAS level. But at least our understanding is that it's not something that you can really reconfigure on radio level.
Okay, thank you.
Then, connected to idle, I guess it's also some sort of simple procedure, very similar to LTE. So basically, is when the UE is in connected mode and receives that release message without a suspend config, it cleans up the AS context, which is basically most of the configuration that the UE had while it was operating connected mode. It released the resources, it stopped timers, and etc. And if you're interested to look at that in the LTE spec, you will find a section called Actions upon going to RRC idle. But in the NR spec, maybe it's a bit confusing here. In the NR spec, this is a different sort of title, actually. Sorry, in LTE it says Actions upon leaving connected. Sorry, in LTE it says Actions upon leaving connected, but in the NR spec we have Actions upon going to idle. So there are some historical reasons for that. But just so you don't search leaving connected in RC, NR, and you don't find anything. And as in connection release in LTE, basically you can include some configuration that the UE uses in inactive state. I think we will have an inactive state presentation, an idle state also, talking a bit more about exact operation in inactive state. But one information, just to give an example, is this redirect information, which is like you can tell the UE, please go away now to idle and select this other frequency, which could happen, for example, when the network is overloaded in one frequency, or I guess in our first product implementations where you don't support mobility, for example. So this is the way that you may get some measurements and you don't want you want the UE to go somewhere else, and then you tell, please go to this other frequency or this same frequency, but to another cell, and then the UE does self-selection in this other frequency. Yeah. Very much like LTE, then network has the alternative to, instead of move the UE to idle, to move the UE to this inactive state. And there I want to start with a story. Here's a bottle of water. I tried to improve that picture and have my own picture, but didn't have much time. So there's a laptop and a bottle of water. And those who know me will get familiar to see, I think, Ashmal, you asked that, why you have this big bottle of water? So I went for some medical procedure, and then I have to drink lots of water these days. And the example I want to bring is that in my laptop, if you could see it, there is a lot of CRs open because I'm doing some CR review this week. And then every time, let's say every X minutes, I have to go to the bathroom, and then I come back. Now imagine that every time I come back and forth, all those CRs are closed, and I have to start my computer from scratch. That would be very inefficient, and I would waste a lot of time. That analogy, to me, is the best analogy to explain this idle to connected, this inactive to connected transition compared to the idle to connected transition. And the reason is that when I come back to my laptop, 99% of the time, I will continue doing exactly the same things I was doing. So there is no point to delete everything and reopen everything again. It's the same story here. So before in this idle to connected transition, most of the things were deleted both on network side and on UE side. But most of the time, the UE was actually coming back and forth in the same cell. And this was actually happening quite often because of the traffic pattern also on smartphones, like these small packets. So this first procedure we saw from idle to connected is quite heavy in signaling. But now imagine doing that every time. So it was very inefficient. So then in release 13, they identified that issue of these many transitions due to the traffic, most of the time in same cell, UE deletes, a lot of info transferred again, and sometimes the same. And there was this motivation, which was the signaling reduction for power saving or a bit more power sensitive UEs. Then they introduced this suspend resume in release 13, where the principle is to restore the UE context, which is basically this information that is either provided by the network or something calculated by the UE, and then later on restore the UE context when the transition to connected happens, such as the security, as I was explaining before. There are some differences compared to the release 13 solution. I guess I just list sort of some of them. The connection of the core network is maintained in inactive state. I think this is not the case in idle with context, like that for the release 13. And then there are other procedures which are supported here, or features which are supported, which are not supported in LT release 13, which is run paging, basically meaning that the UE can monitor, let's say, some sort of paging channel, but with a run identifier. And paging is responsibility of the run. So for the core point of view, is just like forwarding packets to a node. Then there is this RNA updates and the encryption of message 4. I'll talk a bit more about that. So when the UE is moved from connected to inactive state, the UE gets this suspend config, and that's what distinguishes the two cases. And there are two types of configurations that are given to the UE. One type of configuration is IRNTIs and this next hop chain encounter. Basically, this IRNTI is the UE identifier that the UE should use when the UE comes to trying to connect. And this next hop chain encounter is some sort of security parameter that enables the UE to refresh security keys even before the UE receives the resume message. Those are the two new things in NR, I would say, to enable this fast and secure transitions. And then the other part of the configuration is more, let's say, things that the UE is going to use when actually the UE operates in inactive state. Yeah, we have some questions here. Maybe you can start, but I haven't on the chat also. So.
Yeah, so we have a resume ID in 13 just when we do, and now we record this INTI. There's some story behind that. Why is not is it in a kind of similar form of resume ID or is INTI?
Yeah. Okay. So the question was if the difference between the IRNTIs and the resume ID. Yeah. I think the purpose is exactly the same, and that is again an AS context identifier, which is somehow split in two parts, which has something that identifies the UE and another part that identifies where the context is stored in terms of some node, some location in the network side. That's why when the UE comes up somewhere, the target node has means to know, oh, where should I fetch that context? So in that sense, it's the same. The difference in NR is perhaps that you get actually two IRNTIs when you go to suspend. And the reason is that in LT, we have this truncated concept where you have only one sort of long. And then if you go to a cell that for coverage reasons wants to support, let's say, a smaller size of message tree, then the UE somehow knows from sysinfo that it shall truncate. And then it's specify how short it is and which significant bits are shortened and so on. And then in NR, I guess the intention there was to not to specify the details of the structure of the IRNTI, to be a bit more transparent, and instead give two. So then the network has a flexibility somehow to truncate as it wants to, or not even truncate, to give a completely different identifier. So that was a bit the background. In those cases, of the message needs to be shorter. Sorry, I guess we had some. I think it is corresponding to TA. Okay, maybe it's more a discussion. I will not get into that. So if this question, please shout instead of going in the chat. So this is just a couple of actions then when the UE actually goes to inactive, or some concepts, I would say. So in NR, we have somehow be a bit more detail on what the context really means. I think this was a bit of a question in release 13, if you look at the specs, that we say it stores the context, moves the context. I personally, when I started to learn these things, I always ask, what is this context? And I doubt that you can find anywhere what the context really is. Even when you ask the experts, they would say the context is this, this, and that, but you would have never found a place where you have a list of things that is part of the context. If you do, please let me know before release 13. So then the intention here was to be more clear what the context really is, and this is somehow ongoing. There are still CRs trying to clarify this, but in principle, we have in the latest version this. We have the suspend config, which was what we discussed before, this IRNTIs and CC and so on. Parameters configured in reconfigurations or resume. The keys, these are the security keys for encryption and integrity protection that the UE calculates when the UE goes to connected. This ROC state, parameters for resume MACI, which is the security token that the UE is going to use when the UE actually goes to connected again. And the whole point is to say the UE stores this inactive context. Later in the specifications, we say use the context, delete the context, so we go back to that wording again. But at least now in the suspend procedure, we know what the context really is. Then the UE suspends all the bearers except the sub-0 and suspend the connected mode measurements. And then it starts to act in inactive state.
Sorry, can you elaborate like which UE context stored in the UE side and which one stored in the network side?
Yeah, that's a good question. You will not find what is stored in the network side because typically we don't really. Actually, you have to specify because this is a run tree question. Yeah, you have to specify because of the context fetching. My assumption is that it is exactly the same that you have in RRC. Otherwise, you have a problem that is very common when we are specifying this type of procedures, which is state mismatch. So whatever the UE has stored, the network needs to know what the UE has stored, even though the network has the possibility to store something else if it wants to.
Right.
Did I respond to the question?
Yeah, thanks.
So it's a mirror of what you
It has to be a mirror, yeah, at least. Of course, network, as I said, can know more and UE deletes, but it has to know exactly what the UE has stored.
And this is your context that's stored in RRC there or somewhere else?
I guess you cannot really mix these things. I guess it is stored in the eNode B. Let me put it like in some memory. Mm-hmm. RRC layer is more the communication aspect that needs to use. It is stored in some function. Mm-hmm. So if you're thinking CU, DU is split, I would say that it's in the CU, but the DU also needs to know once the UE comes back because there are layer 1 and layer 2 parameters also part of that context. So it's anything that is the UE could be reconfigured with, which includes things which are more DU related.
So it's stored somewhere in the memory, but it's not specific to any of these layers. No, it's not in layer 3.
I wouldn't think so. This is more a round tree aspect. I'm not aware, but I would not think that this detail is really specified. But perhaps there could be some specification of exchanged information between CU, DU when you resume, because some of these configurations are really layer 1, layer 2. But I'm not. I don't know the details of this message.
The parameter for the resume map height here. So actually, whether it is similar to LTE.
Yeah. This is just as an LTE.
The cell ID is ID of the source node.
Yeah.
But I assume that could be out from the resume ID and or INTI here. Not in LTE resume ID is not stored.
I think that's actually, I think my understanding is that this is the whole point is that, I mean, the network could assume, but the whole point is not to assume, because this is what is used to verify if this is the UE, right? And the IRNTI does not really tell what is the source cell. So a UE that, for example, intercepts the message tree and checks the IRNTI does not really know which cell this is referring to as a source, right? The network knows, but the UE doesn't know. So my understanding is that this is a way to sort of verify that, yeah, this UE is really a real UE, because the MAC-I matches, the short MAC-I matches what the source also computes, and the source know where the UE was before, so they have the same sort of. Moving on, from inactive to connected, we have something which is somewhat similar to a certain extent to the resume procedure we have in LTE. Some aspects are different. So as in LTE, the resume request is then transmitted on SRB0. It also contains AS context identifier, which is this IRNTI. It's both used for context fetching in case the UE is actually resuming in a different location compared to where it was suspended, but it's also used for contention resolution as this message tree identifier. Here, I think I responded already to your question. What's the difference with the resume ID? It's like the same. The difference is that we provide 2 in suspend. And as in LTE, it also contains this security token, which is the resume MAC-I, which is like the short MAC-I in establishment. And the intention is to be able to verify this is a real UE, a verified UE, security-wise. So the source then knows, and okay, take the context. So this is a verified UE. It's a sort of semi-verification because this is not really the full MAC-I. There's been lots of debates to have the full MAC-I message tree in NR, but the message tree size was really like a stopper for this kind of things. Then the UE receives, in most of the cases, this RRC resume. It may receive other messages, but we'll not go through that now. It's sent on SRB1. It's integrity protected. I guess what is new in NR is that message is also encrypted. And the idea there was that the UE is going to use this stored MCC received in suspend to refresh the security keys prior to the reception of NR resume message. In LTE, that is not the case. In LTE, you actually receive the MCC in the resume message, and then you refresh the keys. Then the UE resumes the SRBs and DRBs, enters connected, resumes the connected measurements, and they start to operate in connected mode. So that is the timer they use in connected mode. So if you look at that procedure and you remember what we have shown before, after message 4, the UE is in connected mode, and before in the idle to connected transition, there was a lot of things until the UE gets in connected mode. So it's somewhat much more efficient and fast in terms of signaling until the UE can start exchanging data. Actually, even in message 5, the UE can start to multiplex data because message 5 is more like is integrity protected and encrypted. So in a way, it's a way to the network to verify that this UE is really the right UE. But that message does not really contain much stuff.
Another question. Why do you send the IRNTI again? You sent that already in the previous message when the UE was moved to inactive state.
Exactly. I think okay. The IRNTI that you give in suspend is a way that the UE can come back. So it's basically telling this is your address. And then the UE can move around without notifying the network. And then when the UE goes and try to resume somewhere else, this target node thinks, okay, who are you? And that is the question that the IRNTI answers. So the IRNTI tells, I am this UE, and you will know more about me in the second half of the IRNTI, which is the node that holds the context. So when a target node gets the IRNTI, the target node knows what is the source node that holds that context. Then I fetch the context, and then of course that source node also knows, oh, this UE is that UE with that IRNTI. So it's an identifier that allows the UE to move around the network without notifying every time it changes itself. So when I give the network here, basically I'm coming back. Look, I'm coming back, and this is who I am.
Okay, so this is what the UE transmits.
Yeah, this is from the UE. Okay. Sorry, the resume request message 1 there is from the UE to the network.
Okay.
Yeah. We're almost wrapping up. So as I said, the resume complete, there's not much. It's just like LTE, except that there's this dedicated NAS message. This is also a bit similar to LTE in case you are starting some NAS procedure, such as when you're doing tracking area updates and so on. I go very briefly on some of these other configurations. Remember that I said that there are two types of configurations the UE receives when it goes to suspend. One part is to enable this fast transition that we just went through, and the other part is some parameters that somehow tells the UE behavior in inactive state, or sort of are parameters that the UE uses when the UE is behaving in inactive state. This is about this second part. So the UE gets this RNA configuration, which can be a list of cells or a list of TAIs, tracking area information, or a list of RANACs. Basically, in that state, the UE is known in this RNA level at the network side, and the UE can reselect within that RNA without signaling. This is very much related to paging and very similar to how paging works also in idle mode, that you give the UE some area where the UE moves around, and the UE has to monitor the paging channel in every of those cells when it does a reselection. And this is how the network can actually try to reach the UE. In the case of the RAM paging, if some packets from the core network comes to the source that holds the context, then the source does not have the UE anymore because UE is inactive, right? Then the source needs to think, where is the UE? Then the only thing the source knows is the RNA configuration. So then I can page over XN, which is the internode in the run, internode interface in the run. And then these sort of target nodes that are contacted by the source can page the UE. And then you will only see where the UE is when the UE responds. There's someone responded, and then there's context fetch and resume again, thanks to run page. Then there is another procedure, which is this run area update, which can be timer based. So the UE gets this 380 timer when it goes to inactive. And when the timer expires, the UE has to do an RNA update. This is the next slide. It looks very similar to resume. And the whole point of that is in case the UE takes too much time in that state and network is uncertain of what happens, network somehow can always expect this message when this time expires, and if the message doesn't come, network can do some sort of cleanup of the context. And of course, then the other way that you do the RNA update is when the UE reselects to another area. And the reason you have to do that is because you're going away from the area I know where you are. So if I will page you, I will not find you unless I know where you are. And then the UE comes back again when it's outside this area. So this has lots of similarities with how the tracking area update in IDO works.
So that hammer-based kind of access is different from LTE.
Yeah, it is different from. It is different in a way that you don't have RNA updates in LTE, but it's very similar to the tracking area updates in IDO, where you actually have that periodic tracking area updates also. So the difference is that you don't have to contact the core network. You don't do a tracking area update. This is RNA update. One thing that is interesting to highlight is that this is just like resume, and we have a resume cause called RNA update in resume request. Then there has to be some context fetching in one of the flavors, at least. But the difference is perhaps that in NR, because we can encrypt the response message, thanks to the NCC in suspend, we can release the UE immediately, because if there is no data here, there is no point to move the UE to connect it first and then release. So we have that possibility to release the UE directly. And the reason this would have not been possible in LTE is because there are security requirements on sensitive information you give to the UE in suspend, such as the IRNTI, which tells where the UE context is. But in NR, that was possible. And then we did this sort of optimization to do the we call two-step procedure, two-step RNA. You will not find that in RRC spec. It's mainly on 38300 though, because in RRC spec you will just see some sort of, it's a bit hidden. You'll say upon reception of release, if that was because of request of resume, it will be a little bit hidden, but in 38300 you will find it. The other way we use that.
There's actually, since you mentioned that you cannot find it, if you actually look into the EDT that we've been working on in release 15, you can find those concepts. They're all in 36331.
Yeah, but that's for the EDT, right? This is not.
Yes, but just to mention that conceptually, that's pretty much the same thing.
Yeah, actually, it's a good point that you made, because many times when I say it's new in NR, there's no in LTE and so on, I am referring to LTE pre-release 15. And that is mainly because what you said is because of EDT, who actually has quite many concepts from inactive state, but also because LTE connected to 5G core, which also has lots of concepts from inactive state, or vice versa. I think it was a bit happening in parallel when we were standardizing NR.
Mm-hmm.
A last thing is this two-step procedure is also used for release with redirect, or at least this is what we're trying to drive. Basically meaning that when the UE resumes because of some other reason that is not RNA, and we somehow don't want to support that service for some reason, you can immediately redirect. And there is a security requirement also saying that you cannot redirect the UE until security is activated. Therefore, it's only possible if you can actually encrypt the release message, which is possible because of the NCC suspend. So many things actually come from this NCC suspend, which was, for those who remember, big fight in run 2 and so on, and it went according to our way. So that's maybe why I kind of emphasized a couple of times that as a background. I will not have time to go too much into those, but perhaps I will quickly go a few seconds on it anyway, especially in the reestablishment. That is typically happening when the UE is in connected mode. That's first thing to say. It is somehow an optimization that allows the UE to come back when it fails without having to go through, again, this idle to connected procedure, which is heavy in terms of signaling. It's typically triggered when you have RLAP, handover failure, when UE gets an RRC message that is not compliant and so on. It's also transmitted in SAB0 and so on. And the difference compared to LTE is that it is transmitted, the response message is transmitted on SAB1, and it comes integrity protected. And the advantage of that is that it contains also the NCC. And the advantage of that is network can multiplex the reconfiguration message so that the UE can somehow much faster resume the DRBs and SRBs that it has. Another thing is context fetching supports the usage of the CRNTI PCI from source. That was not supported in LTE until release 15 or 14 or something like that. And then we also support the fallback. So there has been some sort of improvements then in the reestablishment procedure. And for those who are familiar will notice that, oh, but this one looks like the resume in the LTE release 13 to a certain extent, but it's maybe not as powerful as resume. I don't think we spend time in reject. This looks a bit like LTE, except some differences on the way we handle the inactive states, that when you are rejected, you can remain in active state. If it's an RNA update, the procedure is pending. So again, we always try to avoid the UE to go to idle, because this idle to connected transition is some sort of heavy procedure. So it's a bit the spirit in many of these. Just to wrap up, this is what we went through. We went through these procedures in the different ways. The only procedure that we didn't go through was this inactive to idle, but that's not the most important. It only happens in many error cases, I would say, when the UE goes to idle and needs to do this so-called NAS recovery. You will find that maybe in stage 2, not much in RRC, but you will see in RRC many times when a failure happens, you will see UE notifies upper layers of a failure, blah, blah, blah. And then when you go to the NAS spec, you will see that upon receiving a notification from RRC, trigger NAS recovery. But basically meaning that when this happens, you will actually go for this heavy procedure where you start from scratch. But we try to avoid that as much as possible. And then you can have this idle to inactive to idle. It could also happen that you are in inactive state, you try to resume, and in this two-step, remember this two-step we talked, you receive a release immediately. And that release could be without the suspend config. And then you could somehow say that you're going from inactive to idle. But if you ask some people like Magnus Statting, I don't know if he's in the call, he would say that no, the UE went through connected in between. But that's more, this is really a deep discussion on protocol modeling that we would not have time to go through. But it's very interesting. Here I just mentioned a couple of references. I mentioned through the presentation, but it's worth mentioning again. We have 38300, which is stage 2. And this is the only place you will find those sort of overview with signaling flows, including internode messages. In RRC is purely UE interface, so you only find UE network. And sometimes it's a bit difficult if you're beginning to understand this, to see how these things interact with each other, because you only see actions upon receiving this message. But okay, but when does UE really receive that message? So I think it's a good exercise to start with stage 2, or maybe asking people when you are interested to know a bit more about these procedures. Very few books about it. It's very difficult to find good books in these high layer procedures. From my knowledge, for detailed UE behavior, go to RRC, and most of these procedures we talked about, you will find in this 5.3 called Connection Control. It's a big bulk on the RRC spec, 1/3 more or less.